Alright, this is our sixth set of notes on the graphical representation of VLE. In this set of notes, we'll focus on McCabe-Thiele or Y versus X phase diagrams. Okay, and we'll look at an example to motivate their application. Alright, and so what I have plotted here on the left, this is our TXY phase diagram that we've been looking at for heptane decane, essentially our idealized system. Okay, and so if I look at this, okay, within the two-phase region, we said we're going to get phase splitting along isotherms. Okay, so remember, pressure is fixed within my TXY. Okay, and why I'm focusing on a TXY is if I think about the most popular vapor-liquid separation process, this can be distillation, and for the most part, our columns could be operating at what could be approximated as constant pressure near atmospheric pressure. Right, and so if I look at my TXY, if I want to find all of the compositions of my liquid and vapor phases, right, I can draw all possible isotherms within my TXY, and I can read off my Y from my dew line in equilibrium with my X in my bubble line. Okay. Now what happens in McCabe-Thiele diagram, or Y versus X, I just take all of these possible YX pairs in this TXY phase diagram, and I plot them. Right, and so what we're going to get is a loci of equilibrium points corresponding to all possible YX pairs that satisfy our equilibrium expression. And then this line here is just a Y equals X line drawn for convenience. Okay, so again, if I draw all possible isotherms, right, so here I take one at this high temperature, right, I could plot it here on my phase diagram. I take another one at a lower temperature, and plot it up here. Right? And so in my McCabe-Thiele diagram, temperature is not constant, but we're going from high to low. Right? And if I recall, if I look at my TXY, low temperatures are what are going to favor the greatest Y in my vapor phase. Right? And so if I think about my high concentrations of Y, they're going to happen over here. Those are going to be my high temperatures. Those are going to be my low temperatures. And as I move to the left, if I move to lower concentrations, that's going to correspond to my higher temperatures up here. Okay, cool. Okay, so that's McCabe-Thiele phase diagram. All right, things to keep in mind is in our TXY, pressure is constant, and then we plotted temperature versus composition. In a McCabe-Thiele diagram, pressure is still constant. Remember, we're taking this data from a TXY phase diagram. Okay. And so what's important to remember is, pressure is fixed, temperature is not constant in this diagram. Okay, what we've done is taking essentially, all of our possible YX pairs from my TXY and are plotting them here as a loci of equilibrium points. Okay, but temperature is not constant; it's increasing as I move from, right to left. If I want to find the corresponding temperature, the idea is, well, if I'm at coexistence, I can find my YX pair at coexistence, and then I can go back to, say, my TXY phase diagram, and for that YX pair, I can find the corresponding temperature. Okay, so remember, temperature is not constant here. Okay. We plot in a Y equals X line, right? It's for convenience for visualizing our McCabe-Thiele diagram, and then it's also going to be useful as a reference point when we draw in our mass balance. Okay. But as long as we plot with respect to the most volatile component, right, it will be that our loci of equilibrium points will lie above my Y equals X line. Right? So this corresponds to Y equals X. So when we plot with respect to the most volatile component, we expect to get a Y that's greater than the mixture we started with. Right? Y is going to be greater than Z is going to be greater than X. We're expecting to concentrate our most volatile component in the vapor phase. And so our curve lies above our Y equals X line. Okay, cool. All right, so here's just our picture of a flash drum. If you think of it in a TXY phase diagram, I start in the liquid phase, and I'm going to increase the temperature to put myself in the two-phase region, at which point I'll get phase splitting, and I'll pull out a vapor phase out the top of my column, which is rich in my most volatile component, and a liquid, which is rich in my least volatile component. Or if I were to picture this in a PXY, you could equivalently think of it as you're going to throttle your fluid so that you reduce the pressure to put yourself in the two-phase region, at which point you would get phase splitting. Okay. All right, so now to motivate the example of a McCabe-Thiele diagram, we're going to take a look at an example problem. So we're separating a mixture of methanol and water in a flash drum at 1 atm pressure. The feed to the drum is 60 mole percent methanol, 40% of the feed is vaporized. What are the vapor and liquid mole fractions and flow rates? The feed rate is 100 kilogram moles per hour, and the equilibrium data is provided in the figures below. All right, and so I have a TXY, then I've created McCabe-Thiele, and I created this McCabe-Thiele by just identifying all my YX pairs by drawing all possible isotherms on my TXY and plotting that loci of equilibrium points along with my y equals x line. Okay, so what I'm going to do next is I'm going to draw a simple schematic of the process in which I have some feed of composition Z1, right? And if I'm thinking about a TXY, I'm going to think about throttling it. So I'm going to reduce the pressure so that I enter my two-phase region and I pull a vapor out the top and a liquid out the bottom. Okay, so again, we're going to picture this in a TXY. So TXY, you might think about heating or cooling that feed, but it's one and the same, right? All we care about is that when I'm in this drum, I have a two-phase mixture, and then this vapor stream is in equilibrium with that liquid at a given temperature and pressure, right? So whether we take that information from a TXY or PXY, it would in theory be one and the same. Okay, but we're going to separate a mixture of methanol and water in a flash drum. Okay, we're given this information, and so the next step is we're going to label it. All right, so the feed is known, the feed composition is known, we know the pressure in the tank, we know the fraction vaporized, right? We're told V over F, and since I know V over F and I know the initial feed, I can use that to calculate my vapor flow rate and my liquid flow rate. Okay, and so the question is, given this information, can I solve my problem? Can I solve for t, y, and x? Okay, and if you were to look at this for a second, if I think about it in terms of what we've done before, if I have a binary system at two-phase coexistence, I have 2 degrees of freedom. And so what we were doing before is if I knew, say, temperature and pressure, and I was at two-phase equilibrium, I could find that isotherm on my TXY, draw it, and I could pull off y and x. Okay. Unfortunately, we just know p, we don't know t, and we don't know x and we don't know y. So in the same token, I couldn't look at my bubble line, find my corresponding x, draw the isotherm to get y, at which point I would have y and t, right? And so if I have a binary system at two-phase coexistence, I have 2 degrees of freedom. Here, we're only given with a single intensive variable, pressure. Right? And so we can't solve it like we did before, right? We're short a degree of freedom. We still have 1 degree of freedom remaining. Okay, and so the question is, well, can I solve it? Okay, and the answer is yes, right? Of course we can solve it, but it's going to be a little different. Right? So what we still have besides our equilibrium expression on this process is we have a total mass balance and a component mass balance. Right? We have 2 mass balances we can write for a binary system. Essentially, we've already solved our total mass balance. Right? We were given F and V over F, so we have F, V, and L. So component mass balance we've essentially already applied, but we still have a component mass balance. And what will happen is our component mass balance will give us a constraint equation which will eliminate that last degree of freedom. And so what we can do is we can solve our component mass balance along with our equilibrium relationship, right? And that'll give us 2 equations with 2 unknowns, right? And that'll allow us to solve our problem. Okay. All right. Now, how do we accomplish that? Well, one might be, if you think back to when we talked about lever rule, I know that I can think about V over F in terms of lever rule, and how I can relate this ratio to ratios of compositions. Okay. And so in theory, what I could do is I could go to my TXY phase diagram. I could guess a temperature. Once I guess a temperature, I could find y and x, and I know z. I could calculate V over F with that guessed temperature and see if my calculated V over F is the same as 0.4. If it is, congratulations, you solved it. If not, guess a new temperature and keep iterating until it converges. Right? You could do that, but there has to be a better way. Okay, and there is. Okay, so we constructed this TXY phase diagram. Right, and so let me just get back there real quick. If I look at my TXY phase diagram, right, I plot y versus x, okay, and what we essentially have plotted is a line of all possible yx pairs that satisfy my equilibrium relationship, right? This is a curve, right? And all the y-x pairs on this curve satisfy my equilibrium expression. Okay? We said we have a constraint equation. Our constraint is our component mass balance. Okay? And what we need to do is we essentially need to find the y-x pair that simultaneously satisfies both our equilibrium relationship and my component mass balance. Okay? Cool. Right? What would be great is if I could also plot all of those y-x pairs that satisfy my component mass balance. Right? And then I could just find the intersection of that curve and line, and I have my solution. And that's exactly what we're going to do. That's the exact reason for which these McCabe-Thiele diagrams were developed. Okay, so if I write my component mass balance, okay, so ZF is XL plus YV, and I rearrange and solve for y, I get y is equal to negative L over V times X1 plus F over V times Z1. Well, I know F, V, and Z1. Okay, this is solved. I know this. L over V is known and constant as well. And so what I get is I get the equation of a straight line of known slope and known y-axis intercept. Okay, and so I can do exactly what we just proposed. Right, I could plot a line, right? I could plot this as a line on my y versus x McCabe-Thiele diagram, and this line would correspond to all y-x pairs that satisfy my mass balance. Okay, and where that line crosses the curve would correspond to the one y-x pair that simultaneously solves my mass balance and equilibrium relationship. Okay, cool. And so then what's going to come on the next slide is, how do I plot a line? Well, the easiest way to plot a line is if I have 2 points, right? If I can find 2 reference points on that line and draw them, I can just connect them via a straight line. My line is plotted. Okay, and so that's exactly what we're going to do. Okay, so the essentially always use most convenient reference point is where this line, my component mass balance, intersects that y equals x reference line that I drew. Okay, and so what I find is where my component mass balance crosses my y equals x line is when y equals x is equal to z. So if I know z, I can just find that point at my y equals x line. There's reference point 1. 2 other common points are my y-axis intercept and x-axis intercept. So here I've solved for both of them. Which one you apply as your second point essentially just corresponds to which one actually lies on my y versus x phase diagram, where both axes just go between 0 and 1. Okay. So if I solve for those 2 reference points, it's my x-axis intercept, which lies on this diagram. So I plot that point. I plot my y equals x equals z reference point, connect those 2 via straight line, and then just draw it out. And where that line crosses my curve, right? This is where my component mass balance, that's the y-x pair that simultaneously satisfies my component mass balance and equilibrium relationship. Right? I just read off y and x, and that's going to correspond to my answer. Right? That's going to be the value of y and x that simultaneously solves my equilibrium relationship and my mass balance. Okay, so that gives me y and x. If I want a t, I could go back to my TXY phase diagram with that pressure, then either y or x, draw my isotherm, and I would get temperature. Okay. Very last thing that comes on here is identifying azeotropes on a McCabe-Thiele phase diagram. So this is acetone chloroform. This is our system with our maximum boiling azeotrope, these 2 components that like each other. Okay. And how I identify an azeotrope on a McCabe-Thiele diagram is, remember, an azeotrope is where my bubble point or bubble line and dew line pinch. And so what happens is my curve, right, my loci of equilibrium points, crosses my y equals x reference point or reference line, right? Because at my azeotrope, y is equal to x, right? And so my curve crosses my y equals x line at the azeotrope, so that's how I identify my azeotrope. And then when we talked about this system, in which we had maximum boiling azeotrope, so if I'm to the left of the azeotrope at low compositions, component 1, which is my most volatile component, behaves like it's the least volatile, right? So the curve's below my y equals x line, and then those rules flip at higher concentrations. Okay, and that's it for our notes on McCabe-Thiele diagrams.